Hello everyone, welcome to the next lecture of Product Realization Technology or Workshop Practice. So in today's lecture, we are going to discuss some advanced materials, advanced manufacturing materials. Before I start the lecture, let me tell you one thing. This is not going to be useful. Whatever we are going to learn in today's lecture, this is not going to be directly useful in your lab, in your experiments, right? Because now when you're learning the first year workshop practice course, you're going to still use more traditional materials, for example, metals, ceramics, and polymers. But these are some new materials. For the time being, you need to learn what these materials are. When we talk about engineering materials, when we talk about materials that are used in manufacturing nowadays, the list will not be complete unless you know a little bit about nanomaterials or composite hybrid materials. And this is the goal of today's lecture, but you will not be directly performing experiments with these materials for the time being. Maybe in some other course in the future you will do that. Okay. So what is the definition of advanced materials? So first of all, this terminology, advanced, that is used for anything which did not exist in the past, but nowadays we are using it. So for example, you can use the terminology advanced for many things. Polymers, some 20, 50 years ago, maybe polymers were very advanced materials, right? Because before that, we only had metals and ceramics. So metals and ceramics, we can call them traditional materials because they're also naturally available. Polymers are also naturally available, but their bulk production, their synthetic production only started not even 50, but some 40 or even 30 years ago. Even today, we are coming up with several new polymers with new properties. For example, shape memory polymers and many other piezoelectric polymers that we discussed in the previous lecture. Even ceramics with piezoelectric properties. So these are also advanced materials because these materials did not exist in the past, and now we actually make these materials with very specialized properties. So properties of metals, properties of ceramics, they are not so much under our control because these materials, they already come with a set of properties, right? So iron comes, for example, with magnetic properties. We can change it a little bit by, say, adding carbon into it, but we cannot change the property or the nature of iron itself. So there we are limited. However, we can, or scientists can, make some new types of materials with well-defined properties, and these materials nowadays are called advanced materials. So the advanced materials of today, in another 50 years, they will probably not so advanced or so new anymore, but that happens to every aspect of technology, right? Okay, so now the materials or the classes of materials that we are going to discuss in this lecture: nanomaterials, composites, and hybrid materials. So these are some terms or some names that you must have heard. Nanomaterials, I'm sure also you even learned some fundamentals in your school days and so on. Composites, maybe you haven't learned, and hybrid materials, well, these are the things I'm going to tell you today. Okay, so let's start with nanoscale materials or just nanomaterials. So what do you understand from nanometer? Everybody knows that 1 nanometer is equal to 10 to the power 9 minus 9, meter. Okay, so this is something which is extremely small. You cannot see it through naked eyes. Even using some microscopes, optical microscopes, the traditional microscopes, you cannot see nanoscale structures. They are so small. 10 power minus 9, you can imagine that is really extremely small unit. Human eye can barely see down to 25 micrometer. Okay, so that is the limit of resolution, resolving two separate things. 25 micrometer is more or less the limit of a human eye, and that is also not my eye, right? I doubt if I can see micrometer at all. So the point is, nanometer, definitely you cannot see or touch or feel. Then how can we have this entire technology now known as nanotechnology, where there's so many nanomaterials being used and so on, right? And how do we make those nanomaterials? And if we make them, how do we know that these are nanoscale materials, or how do we know that we made what we wanted to make? Now, all of these things come under the idea of nanotechnology or the umbrella of nanotechnology. We are going to just talk about nanoscale materials. So if I have a material which is composed of tiny little structural units, and each unit is in the nanometer scale, typically below 100 nanometers. You cannot say 5,000 nanometer. It has to be below 100 nanometer or around 100 nanometer. Then we call that entire material, the set of material, set of these little tiny nanoscale units, that is called a nanomaterial. Okay. Now these units can be, you can always say that every material is made of atoms, and atoms can also be angstrom level or some nanometer scale, you know, 1 nanometer or so. And you can also say that, okay, if we don't think about atoms, at least we can think in terms of molecules. There are several molecules, they are definitely in the nanometer scale. Okay, so then in that case, by that definition, every material is a nanomaterial, right? Because it is made of nanoscale units. Well, that is not the case. Why? Because we call any material nanomaterial only when we have designed that material. We knew what we are going to make, and we have certain properties, certain set of properties in our mind when we are making those materials. So only when they are very specifically designed, then we call them nanomaterials, especially those that are used in technology, for technology applications. Okay, and there are also some other conditions. So number one, these structural units that we are talking about should be reasonably larger than atoms. Okay, they can even be a cluster of several atoms, but still we are not talking at the atom or atomic scale. Or if we take a single individual unit, individual atom as a single unit, that will not work. That does not define nanomaterials, because in that case everything will be a nanomaterial, right? Okay. And number two, also whatever structural unit, as I said, we designed, let's say we wanted to make some tubes which are of nanoscale, or we wanted to make some spheres like fullerenes, right? And they are also in nanometer scale, but they should be more or less uniform when we make the structure. It should not happen that in some other material, if you have some fullerenes, you start calling it a nanomaterial. No, when we very specifically make these materials, we know the dimensions, and within the tolerances, what does tolerance mean? Tolerance basically means how much error can we withstand. So if I want to make something that is 100 nanometer, then maybe 90 to 110 is acceptable. So this 90 to 110, that is your tolerance limit, plus minus 10 nanometer, for example. So within the tolerance, these structures should be uniform in terms of both size and shape. In that case, these specifically synthesized or designed materials, manufactured materials, we call them nanomaterials. Okay. Now, are they crystalline or amorphous? So this is a big question, right? Especially when we talk about manufacturing, everything depends on crystallinity. Everything we always talk about, you know, every processing technique, properties, everything. So in the case of nanomaterials, now we have thousands of nanomaterials. You know, it's not like one or two. It's not just carbon-based materials or silicon-based materials or something based. We have now a lot of materials in the world. Many of them are still in their research phase, but there are like thousands of nanomaterials available in the world at this point. Okay, some of them are amorphous, some of them are crystalline, some of them may have some very strange structure. For example, fullerenes, which, I mean, it's very difficult to define whether it is crystalline because it does not fit in the traditional definition of crystalline materials. But there are even crystals nowadays, for example, like graphene, that is a single layer. So we have two-dimensional crystals. So the definition of crystal and amorphous is also changing as the technology is developing, especially in the nano regime, what we call. Okay, so coming back to the question, are nanomaterials crystalline or amorphous? Well, it depends. Not all nanomaterials are, so there's so many different materials. Some of them are crystalline, some of them are amorphous, and some of them can be even a mixture of amorphous, crystalline, or may have completely different geometries. However, one thing we know for sure is when we have a nanoscale material, then even if, see, you see these pentagons I have drawn here. Let's say these pentagons are some pentagonal crystal structures. Let's say it's a copper nanoparticles or some other metal nanoparticles. They may not exactly be pentagonal, but something like this, crystalline shapes at nanoscale. When we put a lot of them, millions of them together, then to our eyes, they will still look like powders. So in their dry powder state, we are going to use them for manufacturing. Or, you know, manufacturing is again, now you should not think in terms of traditional manufacturing where you use big machines or what you will be doing in your workshop, but here manufacturing can be also making small scale devices, printing, for example, using these nanomaterials. You make an ink out of it. So one thing you should remember is in the large scale, in bulk scale nanomaterials, they are either in some solution form, or they, if they are in dry form, then they look like powders. To our eyes, we cannot resolve nanoscale structures. Okay, so this is another example. There you can have crystals like that. You can also have some tube like structures, which you may have heard a lot. So tubes are typically grown on a substrate, on a support. Substrate is a fancy term for support, right? Like a plate. So these tubes are grown on top of it. Now if I remove them from that support, then again I will have these randomly oriented tubes again in the form of a powder. So when I purchase carbon nanotubes or copper nanoparticles, I will get them in the form of a powder if they are dry, or they can also be sometimes given as a suspension in a liquid. So they are dispersed in a liquid, not dissolved but dispersed. So in that case they are in that suspension form. Okay, so the nanomaterials that you will be using for making anything will typically be in suspension or powder form. Now what do you do with them? What you can do with any powder? Well, there are a lot of powder processing techniques. You also know that for ceramics we use powder processing techniques. Can all of those techniques be used for nanomaterials? The answer is no, but some of them can typically be used. That again depends on the properties and structure of the nanomaterial, right? So what we often do is we mix them with some sort of binder or glue, which is like which is a polymer similar to the glue that you have at home. So glue that you have at home for sticking anything, that's also a polymer, right? So similar glues can be used for mixing that nanomaterial in it and make ink like things, and then you can draw with that. So that is how nanomaterials are used. So this is one most common method of using nanomaterials for making anything for manufacturing purposes. Okay, you can think of other powder processing techniques as well. There is also one name I have mentioned here, lithography, but again that is much beyond the scope of this particular course, some other time. Okay, what else? One more thing that I have written, nanomaterials do not form large scale crystals. So you see again from this example of a metal nanoparticle cluster or set or powder, you may have these nanoscale structures at crystals at nanoscale, but when they are in a large scale, then they are often randomly oriented on top of each other and they do not connect with each other. So if you, random orientation probably reminds you of polycrystalline material. Now you will ask me, why don't I call it a polycrystalline material? Well, polycrystalline basically would mean that although crystals are oriented in different directions, but they are connected to each other. But in this particular case, each individual nanoscale unit is not even connected. If at all it is connected, maybe they are sticking together a little bit, but that is also through very weak van der Waals kind of forces, and in most cases not even that. So here you will not have any order at a large scale. So the order may exist at nanoscale but not at large scale. So that is something you need to remember. Okay, yeah, so this is something we have already discussed, that many materials may have their molecules in the nanometer scale, but we only call them nanomaterials when we very specifically synthesize them, and usually we have these nanomaterials for certain specific purpose with some set of properties. Okay, so now I will end this particular slide here and start the a second part for composites, just to keep the topics separate.